So welcome to class number 10 of basic electronics. So actually it is class number 10 and 11. So today we'll actually start with some problems and then we'll cover some theory parts. So let us do some problems on diodes first. So we have this circuit. There is a voltage source V which is basically grounded here, and there is a resistor R followed by two diodes, and then we have a resistor R2 here and a resistor R1 here, and then we have a diode which is in parallel with this resistor. Okay, and these 3 points are actually connected together. So basically all these 3 points are grounded actually. So this is our circuit, and you are provided with the information that V is equal to 5 volts. So V equal to 5 volts, 5 volts over here, and R2 is 1 kilo ohm. So this is a 1 kilo ohm resistor over here, and we are also provided with the information that V gamma is equal to 0.65 volts for all the diodes. So 0.65 volts, and then we are given another piece of information that this circuit is such that the current ID1 is equal to the current ID2 divided by 2, which is equal to I R1 divided by 2. So this is the information that is provided, and you are asked to find out the value of R1, and you are also asked to find out the value of ID1 and ID2. So ID1 is basically the current which is flowing through this diode D1. So this current is basically ID1, and ID2 is basically this current over here, and IR1 is basically this current. So ID2 is equal to IR1 actually, okay, because they are connected in series. Okay, so you are asked to find out what is R1 and what is ID1 and ID2, provided that this information is actually given to you. Okay, so now first note that this diode D1 is actually connected in parallel with this resistor R2 over here. Now we already argued that whenever the diode is in conducting state, the voltage across the diode cannot exceed V gamma. So if the diode is conducting any current, the voltage across the diode cannot exceed V gamma, which is basically the cut-in voltage. So since this diode is in conducting state, and since a current ID1 is flowing across the diode, this means that the voltage across this diode cannot exceed V gamma, which also basically means that the voltage across this resistor R2 is fixed at V gamma. Okay, because the voltage across the diode D1 is fixed at V gamma, the voltage across this resistor R2 is also fixed at V gamma. So if we call this point as A, let us call it A. So the voltage at point A, VA, is actually the voltage across the diode D1, which is equal to the voltage across the resistor R2, which is equal to V gamma. So the current across this resistor R2 is basically V gamma divided by R2. V gamma is 0.65 volts, which is already given here, and R2 is basically 1 kilo ohm, which is basically given here. So divided by 1 kilo ohm, which gives me 0.65 milliamps. Okay, so we have found out this value of IR2, and IR2 is actually equal to this current ID1 which is asked for. So sorry, now we note that IR1, which is basically the current flowing through this resistor R1 over here, this IR1 is equal to ID1 plus IR2. So this is plain Kirchhoff's current law, which is being satisfied at this node over here. Okay, and ID1 is basically equal to IR1 divided by 2, which is basically given in this equation over here. So we just make this replacement over here. IR1 equal to IR1 divided by 2 plus IR2. So IR1 is equal to 2 times IR2. Okay, so we have already found out the value of IR2 from this equation. So IR1 is basically 2 into 0.65 milliamperes, which is equal to 1.3 milliamperes. So you have found out the value of IR1, the current that flows through the resistor R1. Now to proceed from here, we just write the equation which satisfies the current voltage characteristics of this resistor R1. So we already know that the voltage at the point A over here, this is equal to 0.65 volts, which is basically V gamma. So this is 0.65 volts, and we also know that since these two diodes are basically in conducting state, the voltage drop across each of these diodes is 0.65 volts, which is again V gamma. Okay, so IR1 is basically V is this voltage source over here minus 3 V gamma. Okay, 3 V gamma, one for this diode over here, one for this diode over here, and another for this diode over here. Okay, 3 V gamma divided by R1. Okay, now IR1 we have already found out is 1.3 milliamperes. V is given to be 5 volts, and minus 3 into 0.65 volts divided by R1. So this is 5 volts minus 1.95 volts divided by R1. So R1 is just 3.05 volts divided by 1.3 milliampere, which basically gives me 2.346 kilo ohms. So you have found out the value of R1, and the next thing that is being asked over here is that what are the values of these currents ID1 and ID2. Okay, so ID2 is basically equal to IR1 because the same current flows through the resistor and through the diodes, and ID2 is basically IR1 divided by 2. So ID2 is equal to IR1 equals to 1.3 milliamps, and ID1 is equal to IR1 divided by 2, because half of the current also flows through this resistor over here, which is equal to 1.3 milliamps by 2 equal to 0.65 milliamps. So these three are basically the answers. Okay, so next let us do another problem. So we have this node where a voltage V is applied, and then this current source, and then there is this capacitor C here, and then there is this resistor RS, and then there is this AC voltage Vs over here, and there is this diode D, which is also grounded, and here some output voltage appears V0. Okay, so V0 is basically the AC voltage actually. Okay, not exactly the AC voltage, but let us say the AC component of the total voltage. Okay, so let me write it here. Vs is the applied AC signal, V0 is the AC component of the output voltage. So you are asked to find an expression for V0 in terms of Vs, and you are asked to make an assumption. Assume that the capacitor acts as a short circuit to the AC signal. So you are given these points, and you are asked to find out the AC component of the output voltage. Now note that to find out the AC component of the output voltage, first we have to find out the small signal AC resistance of this diode. Okay, because how much voltage actually drops across this diode depends on the small signal AC resistance of this diode. Now this is a current source actually, and this is an independent current source. So this basically, an independent current source basically means that no matter what the voltage across this current source is, it will always conduct a current of DC value I. Okay, so I again repeat that irrespective of what current irrespective of what voltage drops across this current source, it always conducts the same amount of current. So this is basically not like a resistor. For a resistor, the current is proportional to the voltage, or for a capacitor, let us say the current depends on the temporal differentiation of the applied voltage. Okay, the current source on the other hand, an independent current source on the other hand, basically means that no matter what is the voltage drop across the current source, or irrespective of the voltage drop across the current source, it would actually conduct a constant amount of current. Okay, so this current source basically conducts the same amount of current, and independent current source are basically denoted by this symbol. There is a circle and there is an arrow indicating the direction of flow of current. So this is the symbol of an independent current source. So this structure or this block basically conducts or basically gives the same amount of current irrespective of what is the voltage drop between its ends. Okay, so now in this problem, first of all note one thing, that this current source is basically a DC current source. Okay, and this DC current cannot flow through this capacitor because the capacitor cannot conduct a DC current. Okay, capacitor only would allow AC current to pass through it. So this capacitor cannot conduct a DC current. Okay, so this current source I cannot conduct current or cannot inject current through this capacitor in the steady state. So this path of DC flow or this path of DC current flow is basically blocked. So no DC current can actually flow through this path. Okay, because the capacitor basically blocks any flow of current. Okay, so this path for DC current flow is basically not possible. So I am putting a cross mark over here. Now DC current can only flow through this path. Okay, so this is the path for DC current. Okay, so now we already know that what DC current is flowing across this diode D. So the current that flows, the DC current that flows through the diode, so this D indicates diode and this DC indicates DC current, is basically equal to the current carrying capacity of this current source, which is basically I. Okay, so this small signal conductance GD of this diode is basically I divided by Vt. This we have learned earlier, that the small signal AC conductance of the diode is the DC current through the diode divided by the thermal voltage. Okay, so the small signal resistance is basically the inverse of this small signal AC conductance, which is Vt divided by I. Okay, now let us come to the path of AC current flow. Now when it comes to the path of AC current flow, this AC current cannot actually flow through this path. It is not allowed for the AC current to actually flow through this path, because this is a current source which conducts a finite amount of current of DC value I. So it would not allow any extra current to flow through, or it wouldn't allow any less current to flow through. So it always conducts this DC current I. So it will not allow any AC current to flow through it. So this AC current cannot actually flow through this path. Okay, so this path of flow for AC current is basically blocked. So AC current can only flow through this path over here. So this is the path of AC current. Okay, now we know that in small signal, or for the AC current, this diode is equivalent to a resistor conductor. This we have discussed earlier. This capacitor you have been told to assume to be short circuited at the frequency of Vs. Okay, so when we draw the equivalent circuit, it basically gives us a circuit like this. So we have this voltage source over here, and then we have this resistor Rs. This is grounded, and then there was the capacitor, but the capacitor, it is said that it acts as a short circuit to the AC frequency, and then there is this diode. Okay, there was a current source over here, but again, as I stated, that this path is blocked, so there is no point of putting the current source. So this is our equivalent AC circuit. So this is the equivalent AC circuit, and this diode in small signal or AC conditions, this diode basically acts as a resistor, or this is the equivalent model of the diode with resistance Rd. Okay, so the AC component of the voltage drop across the diode is just V0 equals to Rd divided by Rs plus Rd times Vs, and Rd we have already seen that this is Vt divided by I. So this is Vt divided by I divided by Rs plus Vt divided by I times Vs, and this is equal to Vt divided by RSI plus VT into Vs. So this is basically the expression of V0 which we were asked to find out. So this is basically our answer. Okay. So next let us consider another problem. So this is the third question we are doing today, so Q3. So we are given with this circuit. So this is basically our circuit. We are provided with a voltage V1 here and V2 over here, and we have two resistors of 0.5 kilo ohms each, and then there is a resistor which is 9.5 kilo ohms over here, and we are asked to find out this output voltage V0 for 4 different cases. So V0 for 4 different cases. Case A is V1 equal to 10 volts, V2 equal to 0 volts. Case B is V1 equal to 5 volts, V2 equals to 0 volts. Case C is V1 equals to 10 volts, V2 equals to 5 volts, and case D is V1 equals to V2 equals to 10 volts, and along with V0 we are also asked to find out the value of ID1 and ID2. So sorry, I forgot to put diodes over here. So there is a resistor and a diode actually. So resistor and a diode. So this is diode D1 and this is diode D2, and the current flowing through the diode D1 is basically ID1, and the current which is flowing through the diode D2 is basically ID2. Okay, so let us do case A first. Case A is actually very simple and you don't need to think much to do case A. So it is given that V1 over here is 10 volts and V2 is 0 volts. Okay, now V1 is 10 volts, V2 is 0 volts, this point is grounded, which basically means 0 volts. So the voltage at this point over here must be somewhere between 10 volts and 0 volts. Okay, now if the voltage at this point is somewhere between 10 volts and 0 volts, then this diode D2 is basically reverse biased. Okay, so no current would actually flow through this diode D2 because this is already reverse biased. Okay, now let us call this current as IR. So in this case the current ID1 is actually IR. Okay, because this diode D2 is reverse biased, no current flows through D2. So whatever current flows through this diode D1 also flows through this 9.5 kilo resistor over here. Okay, so here ID1 is equal to IR, and this is basically equal to V1 minus V gamma divided by 0.5 plus 9.5 kilo ohms. Okay, V gamma is basically again the voltage drop across this diode in conducting state. Okay, so this is 10 volts minus, let us assume V gamma to be 0.7 volts, that as I stated, no, V gamma is given to be 0.6 volts actually. So this information is also given, which I forgot to write. So this is 0.6 volts. So this is equal to 0.6 volts divided by 10 kilo ohms, which gives me 0.94 milliamps. Okay, so V0 is basically IR into 9.5 kilo ohms. So this is 0.94 milliamps into 9.5 kilo ohms. So this gives me, let me calculate it here. So this gives me 8.93 volts. So 8.93 volts. And ID2 in this case is basically 0. So these are the three parameters that were asked: ID1, V0 and ID2. So you have found out these three parameters over here. Okay. So now the next question is B, which is V1 equal to 5 volts and V2 equal to 0 volts. Now we are not doing this problem anymore, this question anymore, because this is basically the same as A. The only difference is that V1 is 5 volts instead of 10 volts over here. So this can be done by the same method as A. So just do this problem number B yourself. Now part C is actually a bit tricky, in sense that it is given that V1 is 10 volts and V2 is 5 volts. So here we are actually sure that since V1 is 10 volts, V2 is 5 volts, and this point is grounded over here. So this means that V0 must have some value between 0 volts and 10 volts, but we do not know the exact value right now. So since we do not know the exact value right now, what we can comment is that V1 must, this diode D1 must always be forward biased. Okay, but we do not know whether D2 is forward biased or D2 is reverse biased. This we do not know, but we know that at least D1 must be forward biased, because this V1 is 10 volts, V2 is 5 volts, and then this point is actually grounded. Okay, so we always know that D1 is forward biased, but we do not know whether this diode is forward biased or reverse biased. So we have to make an assumption, and if the assumption is incorrect, we would be getting some fallacy, and then we should make another assumption. So right now let us make the assumption that this diode D1 is forward biased and D2 is reverse biased. D1 is always forward biased, it is not an assumption, but right now let us assume that D2 is actually reverse biased. So D1 is always forward biased here in this particular case. Let us assume that D2 is reverse biased. So if D2 is reverse biased, then we can find out the current ID1 by the same equation as before. Okay, and ID1, if we find out ID1 by the same equation as before, then we have the same current as before. So in this case, ID1 equal to 0.94 milliamps, because we have the same conditions as before. So I1 is 0.94 milliamps and V0 would be equal to 8.93 volts. So V0 is 8.93 volts. Now we see that we have not got any fallacy, or we have not got any contradicting statement, because V0 is 8.93 volts. So our assumption, or our initial assumption, that D2 is actually reverse bias is actually correct, because V2 is 5 volts and V0 is actually 8.93 volts. Okay, so our initial assumption is correct, and hence this diode D2 is actually reverse biased. So let me write it here. Since we haven't got any fallacy, our initial assumption of reverse biased D2 is actually correct. So D1 equals to 0.94 milliamperes, V0 equals to 8.93 volts, and ID2 is 0. Now, if let us say, if for example we would have got, after assuming that D2 is reverse biased, if we would have got this output voltage V0 is 4 volts, then our assumption of reverse bias D2 would actually be incorrect. Okay, because when we have assumed reverse bias D2, after that we have got V0 equal to 4 volts. Okay, and it was already given that V2 is 5 volts. So our assumption that D2 was reverse biased would actually be incorrect, and in that case we would actually have to do the problem assuming a forward bias D2. Okay, so this is how we typically make this assumption over here. Now the fourth case is basically this one, that V1 is equal to V2, which is equal to 10 volts. Okay, so since in this case we already are sure that both these diodes D1 and D2 are forward biased, because V1 is equal to V2, and then both are 10 volts, and this point is 0 volt over here, this is grounded. So the voltage at this node must be somewhere between 0 volts and 10 volts. So D1 and D2 must be in conducting state, so they both are forward biased basically. Okay, so in this case, so in this case, this ID1 is equal to 10 volts minus V0 minus V gamma divided by 0.5 kilo ohm, and which is basically equal to ID2, and IR is basically equal to ID1 plus ID2, which is 20 volts minus 2 V0 minus V gamma, 2 V gamma actually, divided by 0.5 kilo ohms. Okay, now in this case both this loop over here and also this loop over here must satisfy Kirchhoff's voltage law. So we just can do with any loop, and we write this Kirchhoff's voltage law over here. So 10 volts equals to ID1 into 0.5 kilo ohms plus IR into 9.5 kilo ohms plus V gamma, and V gamma is already it is given, it is 0.6 volts. So we have 9.4 volts equals to 10 volts minus V0 minus V gamma is again 0.6 volts plus 19 into 20 volts minus 2 V0 minus 2 V gamma, and V gamma is again 0.6 volts, so minus 1.2 volts over here. So ultimately, if we solve this equation, we are going to get V0 equals to 9.15 volts. So 9.15 volts over here, and if we get V0, we would readily get this ID1 from this equation and IR from this equation over here, and putting this value of V0 in this equation, we can get this ID1 equals to ID2 equals to 0.482 milliamps. Okay, so these are the solutions of the 4 parts, not 4 parts, I have done 3 parts over here. Part number B, you do it yourself. This is the same as part number A basically. Okay, so let us move on to the next problem. So now let us go to the 4th problem. So we have a 10 volt source over here, and then this diode D, which is followed by this resistor R1, then the resistor R2, and then the resistor R3, and then this point is actually kept at minus 5 volts over here. And as I stated, this resistor is R1, this resistor is R2, this resistor is R3 over here, and this point is actually connected to a diode, and this point is grounded here. This point is again connected to a diode and grounded over here, and it is stated that ID2 is equal to ID3 is equal to ID, which is equal to 0.5 milliamperes. Okay, so this is as I stated question 4. So these are basically this diode, this is basically D2, and this diode is basically D3, and so the current flows here, which is 0.5 milliamps, and again this current flows here, which is again 0.5 milliamps over here. Okay, and you are basically asked to find out the value of R1 and R2. So R1 and R2 you are asked to find out. Okay, now let us see what information can we get from this information that is already provided. So we need to extract some information from that. So since this current 0.5 milliampere is basically flowing through this diode D3, which is also written here, this means that this diode D3 is actually forward biased. So when this diode is forward biased, this basically means that the voltage drop across the diode is equal to V gamma. So this voltage drop across the diode is equal to V gamma over here, and again you are asked to assume that V gamma is 0.6 volts for all the diodes. Okay, so the voltage drop across this diode is V gamma. This point is grounded, so the voltage at this point must be equal to 0 minus V gamma, which is equal to minus 0.6 volts. So the voltage at this point must be equal to minus 0.6 volts. Okay, now it is stated that the current through all these three diodes are 0.5 milliamperes. So what is the current that flows through this resistor R3? So IR3 must be equal to ID plus ID2 plus ID3, plain Kirchhoff's current law. So this must be equal to 1.5 milliampere, since each of this ID, ID2 and ID3 are 0.5 milliamperes. So the total current that flows through the resistor R3 is 1.5 milliamperes. Okay. So we can write the current voltage equation for the resistor R3. So IR3 is equal to minus 0.6 volts minus 5 volts divided by R3, which basically means R3 is equal to 4.4 volts divided by 1.5 milliamperes. Okay. Sorry, this point is actually not grounded, but this point is actually provided a voltage of 5 volts over here. Okay, so R3 is basically 4.4 volts divided by 1.5 milliampere. So let me check what this value is. So this is 2.93 kilo ohms actually. So 2.93 kilo ohms over here. Okay, now let us find out what the value of R2 is. So note that this voltage is 5 volts over here, and then a current of 0.5 milliampere actually flows across this diode D2. Okay, so since this diode is forward biased, the voltage across this diode must be V gamma. So this voltage must be equal to 4.4 volts. Okay, so now we know that IR2 is basically ID plus ID2, plain Kirchhoff's current law again, and this is equal to 1 milliampere over here. So the voltage drop across the across R2 is basically 4.4 volts minus 0.6 volts. So this 4.4 volts and this minus 0.6 volts over here, the difference between these two. So this IR2 is basically 4.4 volts minus of minus 0.6 volts divided by R2, and so this R2 must be equal to 5 volts divided by IR2, and IR2 is 1 milliamperes. So 5 volts divided by 1 milliampere over here, which gives me 1 kilo ohm. Sorry, 5 kilo ohms actually. So 5 kilo ohms over here. Okay, so we have got the value of R2, and now we need to find the value of R1. So R1 again is simple, since a current of 0.5 milliampere flows through this diode D. This diode D must be forward biased, so the voltage drop across this diode D must also be V gamma. Okay, and so the voltage drop across this resistor R1 is actually 10 volts minus V gamma minus this 4.4 volts over here. Okay, so IR1, which is basically equal to 0.5 milliamperes, this is equal to 10 volts minus 4.4 volts minus V gamma, which is 0.6 volts, divided by R1. So our R1 is basically 5 volts divided by 0.5 milliamps, which gives me 10 kilo ohms. So we have found out the value of R1, R2 and R3. Okay. So for our next problem, the circuit is basically the same as before. The only difference is that it's slightly more complicated. So you are given with the conditions that V gamma is equal to 0.6 volts, and you are given with two sets of situations. Set A is basically R1 equals to R2 equals to 2 kilo omega, R1 is equal to R3 equals to 2 kilo ohms, R2 equal to 6 kilo ohms, and then we have to find out the value of V1 and V2. So this is one problem, and the next problem is also based on the same circuit, but the conditions are slightly different here. So this is R1 equals to 6 kilo ohms, R2 equals to R3, this is equal to 5 kilo ohms, and you have to find again what is the value of V1 and V2. So these are the two problems here. Okay, and the circuit diagram is actually the same. This is the diode D2, and now here the problem is that we do not know whether this diode D2 and D3 are actually forward biased and reverse biased. We are sure that this diode D is actually forward biased because this is basically connected to the highest voltage source, which is 10 volts here, but we are not sure whether this diode D2 and D3 are actually forward biased or reverse biased. Okay, so here again we have to make some assumption, and if the assumption is incorrect, then basically we would be getting some fallacy, and based on that fallacy we have to make our assumption again. So here we first assume that D2 and D3 are reverse biased, because if D2 and D3 are reverse biased, this makes the circuit easiest to solve actually. If D2 and D3 are reverse biased, no current flows through them, so the current directly flows in this path, and whatever current flows through the diode D also flows through R1, R2 and R3. Okay, so that is why we are assuming the simplest condition. Assume that D1 and D2 are reverse biased. So if D1 and D2 are reverse biased, just as I said, that the current directly flows through the diode D, and then whatever current flows through the diode D also flows through the resistors R1, R2 and R3. Okay. So we assume that D1 and D2 are reverse biased, and based on that assumption, IR1 or ID is equal to IR1 equals to IR2 equals to IR3 equals to 10 volts minus 5 volts. Okay, so minus this minus 5 volts here, and then there is a voltage drop V gamma across this diode. So minus V gamma divided by R1 plus R2 plus R3. Okay, so V gamma is given to be 0.6 volts. So this basically, if I put all the values this R of R1, R2 and R3 from here, I basically get 1.43 milliamperes. Okay, just check this out. I just checked right now that this value comes to be 1.43 milliamps. Okay, but check it yourself. Okay, then this voltage at this node, let us call this voltage to be V1 at this node over here, and let us call the voltage at this node to be V2. Okay, so the voltage at this node V1 is basically given by the equation V1 equal to 10 volts minus the voltage drop across the resistor R1 minus V gamma. So I R1 minus V gamma, and this comes out again to be 6.56 volts. Okay. Similarly, the voltage V2 is equal to 10 volts minus the voltage drop across the diode, which is V gamma, minus this voltage drop across the resistor R1 and R2. So IR1 and IR1 is equal to IR2. So IR1 into R1 plus R2, and this gives me minus 2.02 volts. Okay, so now we note that this voltage V1 is 6.56 volts. Okay, so our assumption, according to our solution, our assumption that D2 is reverse biased is actually correct, because this volts is 5 volts and the voltage here is basically 6.56 volts. So D2 is actually reverse biased. And next, coming to the voltage V2, we note that the voltage V2 is minus 2.02 volts. Now this point is actually grounded, which is 0 volts, and V2 is minus 2.02 volts. So this basically means that our assumption of reverse biased D3 is basically incorrect actually. Okay, so the assumption that D2 and D3 are reverse biased is incorrect. Okay, so we know that D3 must be forward biased, and if D3 is actually forward biased, then this voltage V2 must be equal to V gamma, because in the forward bias state the voltage drop across the diode is always V gamma according to the piecewise linear model. So V2 is basically 0.6 volts now. Okay, so now when we calculate this current IR1, we would not be following the same method as before, because D2 is actually forward bias. So we know that D3 actually, D3 is forward biased, and so V2 is equal to V gamma, which is equal to V2 is actually minus V gamma, so which is equal to minus 0.6 volts. Okay, so there is a minus sign here which I actually forgot to put, so there should be a minus sign here, so equals to minus 0.6 volts. And so this current IR1 is basically 10 volts minus the voltage drop across this diode, which is V gamma, minus V gamma, minus this voltage V2 at this node, so minus V2 divided by R1 plus R2. So this gives us 10 volts minus 0.6 volts minus 0.6 volts divided by R1 plus R2. So if we put the values of R1 and R2 over here, we would get 1.25 milliamps. So 1.25 milliamperes over here, and since we have found out the value of IR1, finding out the value of V1 should not be difficult. So V1 is basically 10 volts. This 10 volts over here. So 10 volts minus V gamma, which is the voltage drop across this diode, minus I R1 times R1. So this is basically equal to 10 volts minus 0.6 volts minus 1.25 into 2 volts, which basically gives me 6.9 volts actually. So this is equal to 6.9 volts. Okay, so we have found out the values of V1 and V2, which were mainly asked. So V1 is basically equal to minus 0.6 volts and V2 is equal to 6.9 volts. Now we need to solve the circuit for condition number 2. So condition number 2 actually states that R1 is equal to 6 kilo ohms and R2 and R3 are 5 kilo ohms. Okay, so R1 is basically 6 kilo ohms, R2 and R3 are 5 kilo ohms, and you are asked to find out the value of V1 and V2. Okay, so like before, here also we do not know whether these diodes D2 and D3 are forward biased or they are reverse biased. Okay, or in which state they are basically. So here again we make the same assumption, and the simplest assumption is basically both D2 and D3 are reverse biased, because that actually allows us to calculate the voltages V1 and V2 without much problem. As I stated that if D2 and D3 both are reverse biased, then the only path of current flow is basically this path. No current flows through the diodes D2 and D3. So this makes the solution much easier. And that is why we are choosing this condition at first. So assume that D2 and D3 are reverse biased. So we assume that D2 and D3 are reverse biased, and just as before, if this condition is not correct, we would be getting some fallacy, and according to which we will be changing our assumption. So here, if D2 and D3 are reverse biased, then no current flows through D2 and D3. So here also ID, just as before, is equal to IR1 equals to IR2 equals to IR3, and this is equal to 10 volts minus V gamma, which is basically the voltage drop across this diode over here, minus 5 volts, which is basically this voltage over here, divided by R1 plus R2 plus R3. Okay, so divided by R1 plus R2 plus R3. Okay, so this gives me 14.4 divided by 16 milliamps, which is equal to 0.9 milliamps. Now from this, let us calculate the value of V1. So V1 is equal to 10 volts minus V gamma, which is the voltage drop across the diode D, minus the voltage drop across the resistor R1. So IR1 into R1. So 10 volts minus 0.6 volt, and IR1 times R1 gives me 5.4 volts. So minus 5.4 volts. So this is equal to 4 volts actually. So we are getting the fallacy that D2 is actually reverse biased, because this voltage here is 5 volts and the voltage V1 is equal to 4 volts. So D2 must be forward biased. Okay, so let me write it here. So D2 must be forward biased. Now if D2 is forward biased, then V1 is no longer kept constant at this 4 volts, but V1 basically becomes 4.4 volts, because since the diode D2 is forward biased, the voltage across this diode is basically given by V gamma. So V1 is basically 5 volts minus V gamma. So 5 volts minus V gamma, so which gives me 4.4 volts actually. Okay, so V1 must be 4.4 volts. So let me write it here. So V1 must be 4.4 volts. Okay, now so if V1 is 4.4 volts, so then we need to recalculate IR1, because according to our previous IR1, V1 would come out to be 4 volts. So IR1 is basically 10 volts minus V gamma for the diode D minus 4.4 volts divided by R1, and R1 is basically 6 kilo ohms. So this becomes 5 volts divided by 6 kilo ohms, and this basically gives me a current of 0.83 milliamps. Okay, now we know the correct current through R1. Next, we need to find the voltage V2, and for that we need to calculate the current IR2 and IR3, so that we can actually understand whether this diode D3 is actually reverse biased or not. Okay, so assuming, so initially we had assumed that D3 is actually reverse biased. So assuming that D3 is reverse biased, IR2 is equal to IR3. So if D3 is actually reverse biased, no current flows through D3, so IR2 is equal to IR3, and this is equal to V1 minus of minus 5 volts divided by R1 plus R2. Okay, so the voltage at this node V1 minus this minus 5 volts divided by R1 plus divided by R2 plus R3. So R2 plus R3. Okay, and V1 is actually 4.4 volts, which we have seen earlier, plus 5 volts, and R3 and R2 both are 5 kilo ohms, so this becomes 10 kilo ohms over here, so this gives me 0.94 milliamps. Okay, and since we have got the current through R2, we can easily find out the value of this voltage V2. So V2 is basically V1 minus IR2 into R2, and V1 was 4.4 volts as I stated earlier, minus IR2 into R2. So IR2 is 0.94 milliamps into 5 kilo omega, because R2 is basically 5 kilo omega as given in this question, and this becomes minus 0.3 volts. Okay, so if the voltage at this node is actually minus 0.3 volts, then this diode D2 is not in a then this diode D3 is not in a conducting state, because to take the diode D3 to a conducting state, the voltage across this diode D3 must be equal to V gamma, or must be at least V gamma. Okay, so since the voltage across the diode according to our calculation is minus 0.3 volts, the diode D3 is not in a conducting state. So our assumption that D3 was actually reverse biased is actually correct. So our assumption that D3 is reverse biased is actually correct. So our final answer is V1 is equal to 4.4 volts and V2 is equal to minus 0.3 volts. Okay, so that's our answer. So let us do up to here today. Thank you all.